We talk about light as a wave. It's easy to forget that all the waves that we usually talk about, like as analogies, are things like water waves or skipping rope waves, string waves, like that sort of thing. And something that we sort of don't acknowledge when we talk about water waves or string waves or whatever is that there's an up and a down. There's an orientation to those waves. Like we just don't even consider it. You're like, yeah, of course they do. But like, how would you orient a ray of light as it flies through space? What defines up? I mean, it's obviously not going to be affected by gravity. We kind of talk about that with special relativity and general relativity. There's not going to be like some sort of an orientation for this wave that's obvious to us. And so that's kind of what we have to talk about today is what's the structure of these waves. So first of all, when we draw a light wave, there's a little bit of a dichotomy. Oftentimes we talk about the directional vector of the photon flying through space. And that would be like this C vector. Look, this light's flying through space. And that would be sort of a particle mentality for thinking about light, right? Of course, we say that it has particle wave duality. So what about the wave part of it? Well, every photon itself could be thought of as like a localized little nugget of wave energy. Fair enough. But what about like the wave orientation? Okay, so another thing that we'd have to think about then is maybe I should choose something that's like definitely a different color than that C vector. We might think about the electric field. And as that light travels through space, it actually has a self-propagating electromagnetic field, as they say, traveling along with it. That electromagnetic field is a fluctuating field. And when I say it's fluctuating, I mean sometimes the electric field is oriented in one direction. But of course, in order to flip over to being oriented the other direction, its magnitude has to die down and then flip and then increase and then decrease and then flip. And so here I am like actually going through the process of showing the instantaneous electric field orientations and magnitudes as this ray of light travels through space. And so I'm going to label that my electric field, my epsilon vector. All the way along, that epsilon vector is not only flip-flopping, but varying in intensity. That's what it would mean to have a wave of electric field stuff. You guys with me so far? I mean, it's kind of an abstract idea, I guess, right? Now, simultaneously, we've also talked about right-hand rules, right? So it makes sense that electric stuff and magnetic stuff are at right angles to each other. And so simultaneously, as that electric field increases and decreases, there's going to be a magnetic field. And this is where the 3D gets a little bit tricky. I'm going to use like dotted lines when I'm in the background and behind that peak, if you like. And you'll say, well, couldn't we get like a better picture of this if we stole it from a textbook? Guess what? That's what I have over here on the right-hand side. Okay, we're actually just going through the process of drawing this so we can get like a tactile feel for the orientations of this magnetic fluctuating wave. And of course, magnetic fluctuating wave is going to have intensities that vary and then orientations that flip. And just like we talked about there being electric fields and magnetic fields in previous units, we're talking about magnetic fields again. And these magnetic fields, I've color-coded them in purple, are our B fields. And so we have a fluctuating B field going through space, the magnetic field. And yeah, we absolutely did just reproduce the textbook thing that I stole from somewhere else, but it's color-coded now, and we've kind of gone through the process of actually drawing it, right? And as we're talking about these fields, we'd say, oh, okay, like in terms of their orientation relative to one another, because we're talking about orientation, the electric field and the actual photon directional vector are going to be perpendicular to each other at all times. What's more, the photon directional vector and the magnetic field will also be perpendicular to each other at all times. And so it's hard for me to sneak in here and draw in little like right angle squares. So I'm just going to make it as a statement, okay? They're always at right angles to each other, always perpendicular to each other. And then on top of that, the electric field, oops, electric field is always going to be perpendicular to the magnetic field at all times. Now, anytime you have a system where all of the vectors are always perpendicular to each other, we actually have a name for that. It's an orthogonal system. Just means everything's always perpendicular. So all those vectors are orthogonal to each other. If you've ever seen the word orthogonal in your high school career, I'd be willing to bet that it probably was like in a drafting class when they had you do orthogonal draft designs for something that you had to put a schematic on. Anybody have to do like an orthogonal drawing before? Really? Okay, well, I guess times have changed. Maybe they just did it in the software for you guys, and I had to do it by pencil and pen. But when I was a kid, but orthogonal drawings going to end up having like everything drawn quite intentionally, where all the right angles are being emphasized. Okay. Anyway, also if you're looking at like interior design, orthogonal design in interior design is one where there's a lot of like perpendicular beams and lintels. You guys ever seen that kind of a house? Think of like old Greek architecture or something like that. There's a lot of orthogonal architecture built into the old Greek stuff, right? Obviously, there's some slanty things too. Pythagoras. Anyway, so we got this whole vector system where everything's at right angles to each other. The annoying thing is this: if I have just an average light bulb, and we'll just like draw an incandescent light bulb. But if I have an average light bulb, there's nothing telling all of those photons that are getting fired off to have the same orientation. That doesn't make any sense. Like, I mean, as I look at all these squiggles, what these squiggles are representing is, in this case, it's just a cartoon. These squiggles will be representing, okay, all the light shining off is going in the same direction from that light bulb, fair enough. But each one of these squiggles represents the electric field orientation for 3 different photons. And obviously there would be like tons and tons of photons, but just for 3 different photons, it looks messy like this because they're all following more or less the same path and they all have different orientations because there's no reason why. Remember, we talked about electron excitation and photon emission. There's no reason why the atoms in that tungsten, that filament, are going to cause the electrons to jump up in energy when they get excited, fall down in energy when they return to their ground level, emit a photon, pew, pew, pew. There's no reason that all those photons are going to fire off in the same orientation. There's nothing constraining that, right? It's going to be chaos. It's going to be total chaos. Let there be light, right? Like the light's going to go off in all these different directions with all these different orientations. And we don't see that kind of thing with ripples on water. All the water just goes up and down because gravity tells it so. And there's nothing to tell light to do that. You guys are buying what I'm selling? Okay. So let's make a little comment underneath of this, just because here I've like ranted a little bit about it. Light can even corkscrew through space. I mean, imagine this. Water waves always have to keep the same orientation. Can you imagine that a photon could fly through space and its orientation could rotate as it flies like a football? It spirals. Oh my gosh, this is crazy. So imagine, a right-handed person throwing a football. A right-handed person would put a certain spiral on that football. Wouldn't a left-hand person put the opposite spiral on a football? So you could not only have changing orientations to the light wave, but depending on how the photon was fired off, it could have a right-handedness or a left-handedness to it. That's crazy. Like there's a lot of variation. You never even think about that because your eyeball doesn't perceive orientation of light. Your eyeball only perceives how bright is it, right? So the fact that you don't have like a nice solid conception of the fact that light can have an orientation isn't your fault. It's your biology, right? So we just have like different perceptions of things. Yeah.
Sorry. Do you have dissection pins?
I don't have any dissection pins in here. No,
Okay.
Sorry. So let's add on to this. So upon reflection, add an extra little dash there. Upon reflection, the corkscrew effect because I don't have like another name for it, but this rotation of the orientation is reversed to rotate in the opposite direction. Maybe I'll just throw in there in brackets, think a spiraling football. When I say football, I mean an American football, not one of those everybody else in the world footballs. Okay? You guys knew that though. All right. Now, having said that, it doesn't always spiral. You actually can have light that keeps its orientation. And if all the light coming from a source is oriented the same way, maybe we'll label this, all photons have the same electric field orientation. The same up and down. That would be a nice simple picture. Would you believe that there are situations where the orientations are equally distributed between all the different orientations? So all the photons have, like an equal amount of up, down, and left, right, and everything in between. We'd call that circular polarization. And then there's actually preferred polarization, where most of the photons, most of the time, are oriented one way versus the other way as they travel through space. We call that elliptical orientation, right? And the ellipse would have its own orientation to itself along its primary axis. Everybody cool with these ideas so far? Like, this is a new way to think about light. Like, I guarantee nobody thought about this kind of concept of light yesterday, right? If you're hearing this for the first time, you've never heard of this before. You've never thought of this before because it doesn't seem like a very natural thing for humans to think about. And when we actually want to produce polarized light, we'd like to transform unpolarized light into, well, for example, the most simple one, that first one in my list, linear, or sometimes people will call it plane polarized light waves, can occur using, there's really two main methods, reflection or transmission through a grating.
I'm sorry, I got
Yeah.
it. The ones that are in the bins are already cut open.
Okay, just give me 1 second. I'm going to go visit some frog dissections. I'll be back in a second.